Hey, welcome back. 2 weeks ago, we started working on this traffic management system project. And last week, we looked at the A-star pathfinding algorithm in preparation for this week's episode. Just a few hours ago, I found out that this pathfinding algorithm is not actually quite suitable in situations where you have hundreds of vehicles querying for their paths. This operation is actually very expensive, and no matter how fast your computer is or how efficient your algorithm is, it still doesn't work. Rather than this week going to waste, I thought I'll just have a look at some very simple harmonic motion and we'll code up a very simple pendulum. Welcome to Code Space. I'm RK. Ravi is still out of commission and is resting on doctor's orders. Hey, welcome back. So as I was saying, Ravi is still out of commission. He's still resting on doctor's orders. But before we go any further, I just wanted to basically say three things. Number one, thank you so much to our viewers. And in particular, I wanted to thank Animesh Ghosh for all of his changes that he did for the A-star pathfinding algorithm last week. So he changed everything he changed the open sets and the closed set to an actual set in JavaScript. It was something that I learned only last week, and I wasn't even aware that sets were available in JavaScript. So I'll just show that to you in just a moment. And that sort of gives me an idea. If any one of you want to showcase your project here at CodeSpace, that will be awesome. I mean, we can show what you've done. We can showcase your code, your execution, whatever you have done. I'd be more than happy to actually showcase whatever you have done. All right, and I also wanted to actually showcase the CodeSpace website that we've built, so that each week's episode you can actually see it working on a website. All right, so let me just switch cameras over here for just a moment, and I have this. All right, so first things first, I wanted to thank Animesh for all of his changes. So the changes are actually merged into GitHub. And what he has done is basically change this open array and closed array into proper sets. So now they're open sets and closed sets. Like I was saying, I wasn't even aware that sets are a thing in JavaScript. You learn something every day. So he's changed that. And I think one of the best things that it allows you to do is to just perform this delete operation. Instead of searching for the array, searching for the element in the array and then removing it from the array, the delete just simply deletes the current block from the open set, and so on and so forth. So thank you so much for your changes, Animesh. It is very rare to have viewers who actually care, and I don't know how to thank you for that. I wish I could have sent you even more calendars. Let me see if I have some left. Maybe I can send you some more so that you can give it to your friends. All right. That being said, I also wanted to show the CodeSpace website itself. It's now up and running. So each week's episode, we go ahead and put it over here so that you can see it happening. So for example, last week's pathfinding algorithm, we changed it so that I just made some small modifications so that the start block remains the same, but the end block, you can go ahead and change it. And you can see that the pathfinding algorithm searches and finds a way to the target. You can look at all of the different projects that we've done. I think something that I'm really proud of is this matrix digital rain thing that we did. It is showing up a little bit big over here, but that's fine. Take another project. This is the 8 queens thing that we did. I also have the other canvas where you can place your own queens and everything over here. The source code for all of this is available on GitHub and everything. All right, so this is like this one place where you can view the episode and also see the canvas running and everything. All right, that being said, what are we going to look at today? So I thought we will just have a look at simple pendulums today. And so what is a simple pendulum? All right, just to make sure that I am okay. What is a simple pendulum? All right, we all know what simple pendulums are. We've all I'm pretty sure in school you've seen this. All right. A simple pendulum consists of a ball with mass m hanging from a string of length L at a fixed pivot point over here. And when displaced to an initial angle and then released, the pendulum will swing back and forth with periodic motion. All right. That's as simple as it can get. Now let's look at the forces that are actually acting on this pendulum. So, the gravitational force G is constantly acting on the bob. Given that the pendulum is displaced by an angle theta, so for example, if this was, I forgot to mark this. So if this angle was theta, then the formula for calculating the motion of a pendulum is generally given as the angular acceleration is G. What is G? G is the acceleration of gravity on Earth. I think that would be 9.8 something meters per second square divided by the length of the fulcrum, length of the pendulum, multiplied by sine theta, sine of the angle by which it is displaced. As simple as that. That's all a simple pendulum really is. So I wanted to sort of code it up and then see how it goes. All right. Now, before we actually start with this one, I also wanted to just briefly touch upon this polar to Cartesian coordinate transformation. All right. Cartesian coordinates, we are all basically aware of it. It's just a graph with an X and Y location, with an X and Y axis, and for example, this location would be 5, 5, that's the X and Y location, 7, 7, 10 by 10, 10 by 3. I hope that makes sense. And polar coordinates would essentially be all of the points on a circle. So if I was to overlay that on a graph, if I had a line of length 6 at angle 30, that the end point over here, those would be the polar coordinates. Basically, where is this point on the circle? That's what it is trying to do. And for the purposes of this simple pendulum, this polar coordinate, this polar to Cartesian would be necessary, because all of our calculations, if you see, because we are calculating the angular acceleration, we'll have to sort of convert it into Cartesian so that we can show it on a two-dimensional plane. So therefore, just keep in mind that the Cartesian x would be sine theta into the radius. So in this case, the x location would be sine of this angle 30 multiplied by the radius, which is 6 over here. And the same goes for y, which is cos theta multiplied by radius. It's just a couple of simple formulas to remember or to make sense. All right. So what do I have in preparation for this? Let me just localhost. I think it's this one. Yeah. So what do I have in preparation for this? Nothing. I mean, I just have a very simple. I canvas. I have a very simple HTML canvas and everything, and I have the init method. And on the init method, I also, I'm just resizing the canvas if it is necessary, and then finding out the width and the height. I also have this acceleration due to gravity already defined. Where did I take this from? I took this from Wikipedia, I think, or a simple search for Earth acceleration due to gravity should provide you what the actual value is. It says 9.81, but I think the more accurate value is 9.80665 on an average everywhere on the Earth. So I just put that. It doesn't harm to give a more precise value and everything. All right. So what do I need to get started with this? Let's just look at this one. It says angular acceleration is equal to G by L into sine theta. Okay. So what is L? L would be the length of the pendulum, or in this case, it's actually called as a fulcrum. So I'm going to call that variable exactly that. So I'm going to say fulcrum length. What do I start it with? Let's start it with 200. All right. So let's say the fulcrum length is 200. I already have G. What should be these? Okay. So I also need, oh yes, one more very important thing that we need to remember is that when you start oscillating a pendulum, the pendulum starts oscillating, and the period of its oscillation is actually not dependent on its mass. So even though in our initial definition we say that the pendulum consists of a ball with mass m, the mass is actually not required to calculate the pendulum's harmonic motion itself. The only thing that it is actually dependent on is the acceleration due to gravity. So that's G and the length of the and the length of the fulcrum. So it doesn't matter. So let's say you had a 10 kg bob hanging by a 10 meter wire. That would have a different oscillation, that would have a different a 10 kg bar with a 5 meter length, that would have a different oscillation. So it doesn't matter what the mass is. If the length is small and if the mass is still the same, the oscillation would be completely different. So it's only dependent on these two. And I think somewhere, and this is where it starts to make intuitive sense when Newton who was Newton? Was it Newton or Galileo who said that it doesn't matter it doesn't matter what the acceleration or what is the mass of an object, they will still fall at the same rate. Basically, the mass of the object is immaterial. I think if you go back to some of those Apollo moon landing videos, there was, I think, Eugene, I forget the name of the exact scientist, he dropped a ball, he dropped a weight and a feather on the moon, and they both fell at the same rate. That the mass is essentially immaterial when it comes to the force of acceleration acting on the object. That was the entire point I was trying to make, and I'm completely lost in this train of thought. Where was I? All right, so we need basically a radius for this bob. So I'm just going to say bob radius is equal to, how much shall I give it? We'll start with 10 and then we'll see how it goes. All right, so we have the bob radius. So basically just to draw the bob, and I also need an angle, right? So I'm just going to call this angle theta. Let's start the angle theta at 0. Is that it? I mean, is that all of the things that I require to do this? Oh yes, I also need something called as the pivot point, or the point at which the pivot is there. So I'm just going to declare a variable called pivot point, which basically signifies where the pendulum is hanging by. So I have the pivot point, and then what do I need? I also need the bob's location. All right, so why do I need the bob's location? So once I have done calculating making this calculation, I'll have to convert it into Cartesian coordinates, at which point I would need the x and y so that I can display it on the canvas. That's what the bob location is. I'm sorry, I'm declaring it as 0 for no reason. It shouldn't be 0. Anyway, so that's the bob's location. Let's initialize the pivot point. Where should the pivot point lie? Let's put the pivot point is equal to new point of, where shall we start it? Say width by 2, which is about half the screen, given by 0 is at the top. So I'll just say 10. So start at 10 pixels away from the top. That's where my pivot point is. What is the bob's location? The bob's location needs to be calculated each and every time. What should it be calculated as? As basically this theta. All right, so I'm going to make that calculation in a separate function. All right, I'm going to create a function called update. The intention of this function is that the update function would essentially calculate the position of the bob and also calculate the harmonic motion as such. So just to begin with, so I'm going to have bob location calculated every time. But just to initialize, let's say, 0, 0. Bob location is a new point at 0, 0. All right. So yes, almost immediately I'm going to have to do polar to Cartesian. So bob location dot x is equal to sine theta, math.sine theta into the radius. What is the radius? Actually, the radius is nothing but the fulcrum length. Let me say fulcrum length. Now, now remember, this bob is actually hanging by the pivot point. So we should add the pivot point's x location to it. That's the x location. And let's look at what the y location is. It's exactly cos theta fulcrum length plus pivot point dot y. All right. Yeah, that's it. So now I have the actual bob's location. Now let's see what happens if I draw it. I'm going to say draw pendulum, which will first perform an update and then we'll start drawing it. Draw what? First, let's draw the fulcrum. All right. So for the fulcrum, oh yes, my context is called pendulum context over here. Pendulum context is equal to, dot begin path, pendulum context dot move to the pivot points X and Y location, right? So move to pivot point dot X and pivot point dot Y. Say line to the bob location dot X and bob location dot Y. Pendulum context dot stroke. So that should draw a line. So that should draw the fulcrum essentially. Let's see if this actually works. All right, so that actually works, but I am noticing two things. One, the fulcrum length is too small. So I'm going to change that. I'm going to say fulcrum length is 400. Now I'm not going to I could make this longer. I'll tell you why. So 400 only reaches like halfway across the screen, but I cannot make it any bigger. The reason for that is because my canvas is only 800 pixels long. Right? If I made it any bigger, I mean, of course I can make it bigger. It's just that when we start swinging it, the bob might just go off screen. I don't want to do that. You're more than welcome to do it if you're experimenting with this, if you download the code from GitHub and then do it. All right, so that's done. What's the next thing? I need to draw the bob. So I'm going to say begin path, pendulum context dot arc, bob location dot X, bob location dot Y. What's the radius? We called it bob radius. Did we call it? Yes, we did call it bob radius. Start angle is 0. End angle is math dot pi into 2. And then this doesn't matter. Anti-clockwise or clockwise, it doesn't matter. And I'm going to say pendulum context dot what? Fill. Let's see. Oh, okay. That bob length is too small. I'm going to say make it 40. Like a nice big bob. All right, it looks heavy, but remember it actually doesn't matter. All right, so before we go there, all right, so the line width is already 2. Yes, so yeah, so there you have it. We already have. What happens if I change the theta to, let's say, 45 degrees? What happens then? There you go. That looks like it's 45 degrees. What happens if I make it 90 degrees? There you go. That's is that 90 degrees? No. Oh, all right. I guess it doesn't matter, but there you go. So that's 45 degrees. So we could actually go ahead and start with 45 degrees. What happens if I was to just increment theta? So if I said theta plus is equal to 0.1 or 0.01 because I wanted to go slow, and if I put a request animation frame of draw pendulum. So basically this thing will now start animating. Now what happens? Oh, it goes the other way around. All right, so I'm going to decrement theta over here. Now the reason why you'll have to decrement is because remember in a graph, X starts from the lower left hand corner and rises up, whereas on a canvas, X starts from the top right hand corner and increments down. So we'll have to live with that. And we also have to clear this, clear the canvas. So let's do that. So let's do just that. Dot clear. It's called clear rect. For a moment there, I forgot the name of the function. So it's clear that, and there you go. So it just goes around. This doesn't look much of a pendulum, but trust me, it's coming. All right. So let's now go back to our formula. What's the formula? Angular acceleration is equal to g by L into sine theta. That's it, right? So I'm going to create, so this is acceleration. This is actually not velocity. Remember, it's gravity that is constantly pulling on the bob. So it pulls it. I mean, there is a force that is acting on this bob that actually pulls it down. But when it gets to its apex on the other end, it starts pulling from that end also. So this formula that you're looking at is basically just acceleration. But there is something called as velocity that is actually in play. So this acceleration needs to be added to a velocity. The velocity needs to be added to the angle, or in this case, our theta. So I'm going to need a variable here called velocity, and I'm going to say velocity is 0 for now. All right. So I have the draw pendulum. Yes. So where acceleration, I'm just going to call it acceleration, is equal to what is acceleration? G. What is G? G in my case is still called G divided by fulcrum length into math dot sine of theta. All right. So that gives me my acceleration. With this acceleration, we add it to the velocity. Say velocity plus is equal to acceleration. All right. And theta plus is equal to velocity. I think that's about it. Are we done? It's going the other way around. All right. So there is a harmonic motion that is being in place over here. But once again, because our y coordinate itself is inverted, I'm just going to sort of put negative g over here so that it looks like it is accelerating down. Oh boy, that's actually quite fast. I mean, maybe the request animation frame is too fast. All right, so yeah, so there you go. So the mass remains the same. Remember how I was saying that the period of the oscillation depends only on the fulcrum length. All right, so you can like sort of get a sense of this. Now let's increase the fulcrum length to 600 and see if that changes anything. All right, so now it's actually quite slower than the other one. All right, and instead of request animation frame, let me just put set timeout, call it after 50 milliseconds. See if that makes a sense. Oh no. So this is still 40 frames per second, I guess. All right. So there you go. So that's actually how a simple harmonic pendulum can work. Yeah, I'm going to say fulcrum length is once again 40 so that you can see it. Now there are obviously other things that you could do to it. All right, what other things can you do to it? You could add damping to it, for example. There are no pendulums on any planet anywhere, or even in space, that just go on and on forever. You obviously have to like sort of dampen it. All right, so I'm going to take this velocity and I'm going to say velocity into equal to 0.7, basically giving it a damping value. Now let's see what happens. Oh, it immediately stopped. That's because it's almost as if this pendulum is in honey or in water or something. I'm going to say 0.9 and see what happens. Oh boy, even that. Okay, 0.99. All right, so there you go. So that's a very simple pendulum. So yes, so hopefully a shorter episode today. But I'm going to switch back cameras over here for just a moment. So that's all I wanted to showcase today. Just a very simple pendulum, just some very simple coding to achieve harmonic motion on canvas and in JavaScript. We will make use of this at some point in the future, because what I also wanted to do was take this pendulum and sort of also create a Newton's cradle. At some point in the future, we'll also be playing a lot with these forces. I have plans for making something called as a Galton's board, Newton's cradle, just some other canvas or JavaScript related projects that have got to do with forces and things like that. So even though this was a very simple project, a very simple episode today, this will lay the foundations for later projects in mind. That's all I had to show. Thank you so much for joining. And once again, thank you for our viewers, and especially Animesh for making that change last week. Thank you so much.